Hello everyone, welcome to this NPTEL course on Advanced Pre-Stress Concrete Design. Today we will be starting this new module which is 4.1. We are going to deal with Flexure, mostly focusing on the analysis. Right, so what are the expected learning outcomes of this module? The student should be able to explain the basic theory of Flexure, and then the student should be able to determine the maximum stresses under service conditions and transfer conditions using the stress concept. There are three concepts of analyzing a pre-stress concrete section and member. Then we will also move into C-line or force method of analysis. Student should be able to explain what is a force method and how force method can be used to calculate the stresses, and then the equivalent load method for calculating the load balancing method. So we call that as a load balancing method. The student first need to calculate the equivalent loads, and then from using the equivalent loads we can do the analysis. Right. So let's first, before we get into the Flexure, let's just briefly brush up on the fundamentals of elastic beam theory. You must all studied in your undergrad courses. You know, if you take a beam like this, and if I discretize this beam with horizontal and vertical lines, when it is subjected to a load like this in the middle, then you know that when the beam is undergoing bending, and these vertical lines are basically going to rotate, and the horizontal lines are going to either stretch or get compressed, depending upon whether they are in the compression region or in the tension region. The important point to note here is the vertical line remains straight and it is just rotating. So that's the basic fundamental assumptions in bending theory. You all know that. That's what it dictates. The plane sections normal to the beam axis remain plane after bending. That means an initially straight beam strain varies linearly over the depth of the section. So the strain variation is always linear. So this is what we are going to assume even when the cross section is undergoing at ultimate stage. The strain variation is always going to be varying linearly, and this is valid for slender members, which are where the cross section dimensions are smaller than the length of the, considerably smaller than the length of the member. But whenever we go to the deep beams, then this linear strain variation is actually not valid. Then we have to include the deformation that is coming from shear as well. Okay, what are the other assumption that we are going to make? The maximum compressive strain the concrete is going to take in bending is limited to 0.0035. This is as per IS codes. Okay, this is as per IS codes. But ACA code, if you look at it, they limit the strain as 0.003, but Indian codes typically in pure bending or bending dominant behavior, we take the maximum compressive strain as 0.0035. Now, when we talk about the flexural analysis, now we are going to do two things. The first part, using the actual material models, we are going to study the moment curvature behavior. For that, the parabolic model that what we talked about will be used in the material chapter, which is also the Hognested parabolic model. We are going to use it. And then when we do the design, we are going to use the design stress strain curves for concrete in compression that is recommended by the code, will be used for design purposes. So we have already studied what are the difference between them in the material chapter, so you can go back and look at that particular part of the module. Similarly, the tensile strength of the concrete is ignored because here we are talking about normal reinforced concrete, not fiber reinforced concrete or other special concretes. In a typical normal reinforced concrete, tensile strength is going to be low. It varies from 5 to 10% of the strength of the concrete, and the strain at which it is going to crack is going to be very, very low. So that is the reason it's reasonably a good assumption, because the area over which the stresses are going to act in bending is going to be small. So it's not really going to contribute much in terms of strength or other properties. Now again, for part 1 behavior, we are going to use elastic plastic or elastic bilinear curves, stress strain curves for steel, and for design actually the representative stress strain curves from IS-13 will be useful. This is for steel. For steel, we are going to use, for both non-prestressed steel as well as prestressed steel, we are going to use a bilinear model. It could be elastic plastic or elastic somewhat linear hardening behavior. These two curves that we will be using for design purposes. Okay, let us briefly review this basic bending theory. Let us take this simply supported beam, and it is subjected to 2-point loads like the one that we see here. And if I take a section at a distance x like this, what we are seeing at a distance x, if I take a small elemental length dx and then look at what is happening because of the load, you will find that when before deformation, that means when P applied is 0, if you take the cross section, you know that if I take this neutral axis, the neutral axis is the location where the deformations are going to be 0. If I take the small element length, that is going to be dx, and if I take another fiber which is ds at a distance of y from the neutral axis. So, this is your neutral axis. So, we take this is before deformation, right, and y is always measured from the neutral axis. As you go away from the neutral axis, the distance of the y is going to be larger. Now, after deformation, that means when P is applied, let us say about 100 kilonewton or so, just for example, right. Now, this particular element is going to deform, right. So, and we know that this is going to create a bending moment, which is going to create a sagging bending moment like this, M and M here, and this segment is going to bend and it is undergo curvature. So, if you look at here, this distance, what we are saying is from here to here is, if I take that as r, now this dx is the elemental length at the neutral axis, whether load is there or load is not there, dx will remain same. But however, a fiber at a distance y from the neutral axis now will become ds prime, right. So, if I draw this straight line of the deformed member, they are going to meet at a distance somewhere here, and they are going to subtend an angle d theta between them. So, this is the way that elemental rotation has happened for the small elemental length dx, that is that we have taken, right. Now, you can use your simple definition of a strain, and we can now calculate what is the relationship between curvature and strain and the distance of the fiber, that what we are taking. So, that is what we are trying to find. Then we will try to find a relationship between curvature and the deflection. So, these are the two things that we are trying to establish. Then we will also find relationship between curvature and the applied bending moment. Okay, so from the basic definition of a strain, we know that this is going to be change in length by original length, which is ds. So, ds prime is after deformation, ds is before load application. So, ds prime minus ds will give me change in length by original length will give me the strain. Now, I want to also calculate the distances ds and dx. You know that before deformation, both length ds and dx are same, they are equal, and now we know that dx in this equation, if you see, that dx is nothing but r into d theta from circular bending. If this element is undergoing a circular bending, if I assume this deformation along the neutral axis to be a circular, right. So, you can take this as dx as r into d theta, right. So, now we calculated ds and dx is equal to r into d theta. Now, I want to calculate ds prime. So, you know what is ds prime. Now, this distance is nothing but, from simple, we know that it is going to be r minus y. Similarly, ds prime can be written as r minus y into d theta. So, you got these two values. Now, put it in this basic equation for strain, then you can find a relationship between strain and the radius of curvature, where r is nothing but your radius of curvature. Okay. and curvature is nothing but the inverse of radius of curvature. So, you can find that curvature is nothing but strain divided by y, the distance of the fiber. Okay. So, this is again the strain, we are measuring it at a distance of one element length at a fiber at a distance y from the neutral axis, right. So, we can say that the relationship is nothing but the curvature can be defined as the strain in the fiber divided by the distance of the fiber from the neutral axis, right. So, this way we can establish a relationship between the curvature and strain. Now, we need to look at how we develop the relationship between curvature and the applied bending moment. Okay. So, again 1 by r is nothing but curvature, typically curvature is denoted as phi or phi, however you want to call it. So, 1 by r is nothing but your curvature, which is equal to epsilon by y. Okay. Now, let us move on. Now, we have to establish the relationship between bending moment and the curvature. Now, if you take the small cross section, right, and if these are the axis notation that I take, x along the longitudinal length, y along the vertical direction, z is along the orthogonal direction to x and y, right. Let us say that for this particular cross section in 3D, it is subjected to 3 internal forces. One is the axial force, another one is the shear, another one is the bending moment. Now, we are going to focus only on the bending moment and the axial force. So, let us look at it now. Now, if notations, if you know sigma xx, when we say this is the stress acting on the x plane, that means on the plane that is perpendicular to x axis. In the second indice, x denotes the direction of the stress. So, that is sigma xx. So, sigma xx is the stress that is acting on the plane that is perpendicular to x axis and it is acting in the x direction. Now, if you look at it, this small element that is highlighted, we can also calculate this area if you take this as dA, which is going to be equal to d into dy for the cross section, that is what we consider. Now, we know that force is nothing but stress into area. So, sigma xx is a stress into elemental area, which is b into dy, will give me the force that is acting on this shaded area. Now, I want to calculate the force on the entire cross section. So, I have to integrate it. If I take my reference axis as from the neutral axis, I have to integrate until plus h by 2 and then downward I have to integrate it up to from 0 to minus h by 2. So, the lower limit is minus h by 2 and upper limit is plus h by 2, right. So, this is the way we get. Similarly, shear force can be calculated as sigma xy into b dy and the entire integration. Now, how about bending moment? Bending moment, we know that again it is force into the distance of the force that at which it is acting. So, again we can calculate for each elemental strip that we have taken, how much is the force that is generated and what is the distance at which it is acting. You know, the force remains same, sigma xx into b into dy, but that element area we can say that I am taking at a distance y from the neutral axis. So, your lever arm is going to be again y. So, in this way I can calculate the applied this is from your moment equilibrium, right. So, sigma xx into b dy into y will give me the moment equilibrium equation, right. Okay. Now, let us go back. So, we know that for elastic material we can write stress and strain are proportional, they are related by the elastic modulus E, right. So, now we also know the relationship for epsilon that we have calculated as 1 by r is nothing but minus of epsilon by y, depending upon the sign convention that you have taken, or in other words curvature is nothing but strain divided by the distance of the fiber where the strain is being calculated. Now, we can just replace epsilon xx as y by r. So, sigma xx becomes E into y by r, and if you substitute in this equation, we say that this will become y by r into E into dy dy. So, I have just replaced sigma in terms of strain and the strain is replaced in terms of curvature. We know that strain is equal to y by r, right. So, when you do that, you will also find that you can replace this as, we know that b into dy is nothing but dA, and y when I multiply it, it will become y square into dA, and all the other constants which we can take it out, which is nothing but your E by r square root of minus h by 2 to h by 2. This is nothing but you are going to be y. Now, from your basic strength of materials, sectional properties you might have already studied. This, the integration of minus h by 2 to plus h by 2 y square dA is nothing but your sectional property, which is nothing but your moment of inertia. So, finally, we can write the relationship this as y. So, that is the reason that you will get this as y, then you will get this relationship, which is m by ei is equal to 1 by r, right. And this is nothing but your curvature of the section. Curvature is nothing but how much the section has actually rotated, right. So, you are basically calculating the if the strain at the neutral axis is 0, if at a distance of fiber there is some strain, that strain divided by the distance is nothing but how much actually the strain, the particular section has actually rotated, right. So, this is the way we can say. Now, for any particular curvature, this, when the E and I remains constant, this becomes elastic, but in a reinforced concrete system, E will not be constant, because the material, if you see the stress strain curve equation, the initial portions of the concrete stress strain curve in compression is only elastic. When the stress becomes more than 40% of your peak strength, then the curve becomes nonlinear. So, E is not going to be remaining constant. Similarly, I, the moment of inertia, you know that under service loads, the concrete sections will be cracked, and but in design we only limit the crack width, but we do not completely avoid the crack. So, I will not be complete gross moment of inertia. What we have to use is a cracked moment of inertia. However, still the linear bending theory is valid for when the section is undergoing inelastic stresses and strain as well, and this strain distribution is still considered to be linear. So, we can use this to calculate what is the curvature, but only thing is I have to modify the E and modify the I, or I have to use the nonlinear constitutive equations to calculate my stresses. Okay, that we will see in the coming modules how do we do that. Okay, now that we got this dx is equal to r into d theta, and we can write r as 1 by r, or in other words d theta will be equal to 1 by r into dx, and 1 by r we know that it is equal to your curvature m by ei. So, d theta is nothing but m by e into dx. This is what you must have studied in your moment area theorem also, right. So, we load the beam as a curvature diagram, which is nothing but m by ei. For elastic system, m by ei is nothing but your curvature if E and I are remaining. I is uncracked and E is remaining in the elastic regime, m by E is nothing but your curvature diagram. Okay. Now, if you choose this axis, let us say that my deflection I consider that as V, okay, as we have seen here. Let us say this is my deflection, which is V, okay, and let us say that if I consider this, choose the axis positive as upward, and if I want to establish this curvature in terms of distance x and V is your displacement, or you can say deflection in a beam, then we can, the elastic curve, you can for a beam that is undergoing a curvature, from the textbooks on the calculus, we can say that the radius of curvature, or 1 by r curvature, is written as d square v by dx square divided by 1 plus dv by dx square to the power of 3 by 2. But we are going to, in strict sense, this is the equation for the curvature, okay. Again 1 by r is curvature, r is radius of curvature, right. So, you will have both of this, but in reality beams, concrete beams, or as a matter of fact any structural member, the deflections are considered to be small. Okay, what is the meaning of how small is small? And if you see, typically we don't subject the beams to more than 30 millimeter or 40 millimeter, in a usual practical regime, right? So, but if you look at compared to the length of the member, the deflections what they are assumed to undergo is going to be very small. So, we say this as a small deflection theory. In small deflection theory, if the deflections are going to be very small compared to the length of the member, then the dV by dx term can be considered to be nearly 0. Then we can take again 1 by r is nothing but m by I. So, we express this. Then since the slope of the elastic curve for most structures is very small, we use small deflection theory and we assume that dy by dx is approximately 0. Then this equation will become d square v by dx, because this will become 0, the entire thing will become 1, and now we can simplify m by I or curvature as just the second derivative of your deflection with respect to x. It is a very simple expression for relating the deflection and the curvature.